you. Now let's do if I can do the share screen. It even looks like fine. Okay, so let's hope that we will not have many technical problems today. Okay. So indeed, today we continue to discuss cosmology. We won't finish it today, so we'll proceed next week. And next week, I think, is going to be the last week of teaching this semester. I'll see if we'll see how we progress. Either we do cosmology the entire next week, or I might have like one lecture to do gravitational waves, which one lecture is certainly not enough, but could at least give you something about that. And as I promised, by the end of this semester, you will know enough that even if we don't talk in the course about gravitational waves, then it will be pretty easy for you to open up a textbook, read it, and understand what's going on there. Okay, so what did we do? So we talked about the Robertson-Walker metric. ds squared is minus dt squared plus a squared of t times dr squared over 1 minus kr squared plus r squared d omega squared. So this is a metric that describes a universe which is homogeneous and isotropic in its spatial part, but it can change with time. And the way it changes with time depends on this parameter a of t, which is known as the scale factor. And we said that this universe that we're talking about is a maximally symmetric. And we said that there are three options for that. So there's this curvature k, which can take any value, but really we're interested in only three values because any other value can be absorbed into the coordinates and the definition of a. So we can have a k equal to -1, 0, or +1, right? So the -1 is a negative curvature, and then the universe is called open. 0 is a flat universe, and +1 is a closed universe. This is the most general metric. And then we plugged it into Einstein's field equation, and we ended up with an equation that described the evolution of this scale factor a of t, which multiplies all the spatial coordinates. So Friedmann equations right? A dot dot over A is equal minus 4 pi G over 3 rho plus 3P, where rho is the energy density and P is the pressure in the universe. And then A dot over A squared is equal 8 pi G over 3 rho minus K divided by A squared. So these are the two Friedmann equations. And then we proceed and define the Hubble parameter. H as the rate of change of this scale factor. And the deceleration parameter Q as, again, the rate of change of the expansion, really. So minus A dot dot over A dot squared. And we said that the Hubble parameter today is known as Hubble's constant, though it's not really a constant. Hubble parameter today. In cosmology, today is denoted as 0. Everything we say 0 is what happens now. T0 is 67.66 plus minus 0.42 kilometer per second per megaparsec. Megaparsec is a unit of length in cosmology. And this is a measured parameter. We'll discuss that later. Now, we wrote down the Friedmann equation using the Hubble parameter. Sorry, after defining, okay, then we defined the critical, so one thing at a time. Then we said, okay, using Hubble's parameter, we could write down Friedmann's equation as 1 is equal 8 pi g over 3h squared rho minus k over a squared h squared. This is the second of Friedmann equations. And then we define the critical density. It's really an energy density, right? Rho critical as 3h squared over 8 pi g. And then the density parameter as omega is equal rho over rho critical. And then Friedmann equation again became omega minus 1 is equal to k over h squared a squared. And so we saw that the measurements of this critical density and the density of the universe is actually essential in determining the global property of the universe, right? For if rho is smaller than rho c, that implies that omega is smaller than 1. And that implies that k has to be negative because h squared and a squared are both positive. And that means that we live in an open universe. If rho is equal to rho c, that means that omega is equal to 1. That means that k must be 0 and the universe must be flat. And if rho is greater than rho c, then omega is greater than 1, and that is k is equal to plus 1, and that means that the universe is closed. So there is a big, huge importance in measuring the exact value of the critical density. And the surprising result is that the current measurement is actually consistent with all three possibilities. So the best measurement is that omega is 1.0023 plus minus 0.0055. What I know, last time I checked was like 2 years ago, so. Which is not a trivial result at all, because we're measuring, the Hubble's constant really tells us the expansion rate of the galaxies. The density that we measure is the energy density, right? So we measure that by looking at the density of matter, of stars, of radiation, and there is nothing really that, I would say that omega needs to be consistent with 1. We could get any number. It would be much different than 1. It could be 1,000. It could be 10 to the minus 4. But no, it's a 1. Well, consistent with 1. So this is it's a mystery. We don't know. That's why that's kind of giving origin to additional theories, which I don't know how much time we'll have to speak about. I may, if you want, speak about inflation and other theories of that kind. So that's where this is one of the origin. Then the next thing we spoke about was about the content of the universe. again, not to be confused, right? We're talking about the context of the universe on a very large scale, right? So scales which are much greater than the scale of a galaxy, much greater than the scale of clusters of galaxies, definitely much greater than the scale of the solar system. And we said that in the universe, we really have only three ingredients that we know of. One of them is matter, normal matter, which is described by the equation of state. And all of them are described by equations of state, right? So equation of state is that P is equal omega rho. And then we add the conservation of energy. With combined with the equation of state, we wrote as rho dot over rho is equal minus 3, 1 plus omega A dot over A, which could be integrated to give rho proportional to A to the power minus 3, 1 plus omega. And then we said, okay, what do we have in the universe? So the first thing we have is matter, for dust, which basically have no pressure. So it's a zero pressure, which means that omega is equal to 0. And that's called the matter-dominated universe. In which case, the energy density proportional to A to the minus 3, which is taken directly from the general equation of conservation of energy, with 0 omega. So that's to be expected. As the universe expands, then the scale factor multiplies all the coordinates. The matter cannot be produced or cannot be destroyed. So simply the density of matter and the density of the energy of the matter goes down as the 1 over the volume or 1 over A cubed. So that is one option. The second option is radiation. When we say radiation, we mean, of course, photons, but also relativistic particles, everything that moves at relativistic speeds. And then we show that for those, the equation of state, P is equal rho over 3. There are various ways of seeing that, and I think you might have already been deriving that in one of your previous courses that I do not know. Anyway, I gave you two derivations for that. That means that omega is equal 1/3. And that means that rho radiation drops as A to the minus 4. Again, using the same equation. Again, on the one hand, that makes sense because when we speak of a box filled with photons, relativistic particles, as the box expands, right, then the density of the particles expand, but also their energy of an individual particle go down. And you can think of it as the velocity goes down. Which means that the energy density in radiation goes down faster than the energy density of matter. And this is important when we look at the history of the universe, because we know that the universe expands, which means that the scale factor A of t grows with time. And today we know that the universe is dominated by matter in terms of energy. That is, the energy density in matter is much greater than the energy density in radiation. But it was not always like that. There had been some time in the past where the universe was dominated by radiation. This, as we'll see today, this will affect the evolution of the scale factor of the universe. But then there is a third component, which does not have any simple analogy from things which you have encountered in every day or in other courses in physics, and that is the vacuum. So we said there is a vacuum which has some energy, contains energy in accordance to the extra term in Einstein's equation, right? G mu nu is 8 pi G T mu nu minus lambda G mu nu, which we can think of as T vacuum, it's just minus lambda over 8 pi G G mu nu, in which case we have that rho vacuum just minus P, which is just lambda over 8 pi G. So this is something which is, you don't really have any intuition for that because you don't see it in everyday life, right? It means that omega is equal to -1, right? So, that means that the more energy you have, the less pressure you have, which is completely counterintuitive, right? Or you try to increase the pressure, then you're decreasing the energy, which is completely opposite to what you're used to when you think of everyday things that you're seeing, like particles, matter, radiation, whatever. And that means when you put omega equal to -1, that the energy density of the vacuum, rho lambda, goes as a to the power of 0. So essentially, it is not changing with the scale factor. And since the energy density in radiation and matter goes down, that means that sooner or later, the dominant content of the universe will have to be that of this vacuum energy. In fact, it already has been started to be, not so long ago in cosmological terms. Right. I think that's as far as we managed to. Oh, this is said that this is radiation dominated. This is of course called vacuum dominated universe. Now, in fact, today, from the best measurements that we have, about 70% of the radiation in the universe is here. It's the vacuum. And the rest mostly is about the matter. Actually, it's called cold dark matter, omega lambda CDM. That's why the universe we live in is called lambda CDM. We have omega lambda is about 0.7 measurements. Omega or CDM stands for cold dark matter. It's about 0.3. And out of that, omega baryons are the material that we know of. It's about 4%. It's likely more, between 4 and 5%, 0.0486. And omega radiation is something like 10 to the -5 or something. It's really negligible. So that's why we said that we live in a lambda CDM universe. Lambda is the vacuum and CDM stands for cold dark matter. Now this is pretty much as far as we managed to go to last time. So before we proceed, I would like to stop and ask you if you have any questions.
Stuff?
Yes.
Didn't we say that T mu nu in vacuum is 0 at the beginning of the course?
No, I meant the cosmological constant, right? There is an extra term which you can plug into Einstein's equation. You don't have to put it there, right? But you can add an extra term to Einstein's equation, which will not change the equation, right? This is the cosmological constant or the dark energy, okay? It doesn't have to be there, but you can put it there. And I told you that initially, I told you this story, which is a very famous story, right? That initially, when Einstein wrote his equation, he didn't need that, but then he realized that his equation does not give rise to a steady universe, but to an expanding universe. And at that time, he believed that the universe must be steady. So he realized that he can add this term by hand, essentially. It's mathematically consistent. And if you add it by hand and you put down the right value, then it can be can get a steady state universe, although this is not a stable. So every small perturbation will take you away from stability. And after Hubble discovered that the universe is expanding, it just said, okay, that was a mistake, I should put that. And it was disappearing. And then the lambda one is something which is entered now. This is the new result with the accelerating universe. This is a result which was done by the Hubble Space Telescope. By the way, I don't know if you heard the news, they have some malfunction in the Hubble Space Telescope now this week that they discovered. It's not clear if it would continue to operate or not. But this is something that the Hubble Space Telescope discovered in 1999, so slightly more than 20 years ago. And this is the Nobel Prize for Perlmutter and Adam Riess, and I don't remember who was the third guy, for showing that there is actually an acceleration of the universe. As the only way that people can explain it within the context of the standard model is by adding this extra term, which again can be there. Or you can think of another theory, but that's your responsibility. Right, did I answer?
Yes, thank you.
Okay. Any more? Any more questions? No? Okay. Let me write down back the Einstein's Friedmann equations. Right? So the Friedmann equations, I just want to copy them. So the two equations, A dot dot over A is equal minus 4 pi G over 3 rho plus 3P. And then A dot over A squared is equal to 8 pi G over 3 and rho minus K over A squared. Now, in principle, we can solve them, right? If you tell me what is rho and P, or you tell me the equation of state, and we know what is K, then this is solvable. This will tell us how the scale factor A evolved in time, right? Now, rather than having a full solution, which is a bit tedious and annoying, especially when you have all sorts of various omegas, we can look at the specific examples, the simple examples, which will tell us a lot about the general evolution of the universe. So the title of what I'm going to say now is called the Big Bang. Not the TV show, but the real one. Big Bang. Let's say bang. Big Bang. Okay. So we start with a simple universe. So let's say that we have lambda equal to 0. Okay. Now, let's look at the universe that has a positive energy. So assume lambda equal to 0, have a positive energy density, right? No, like strange particles that have some sort of negative energies, and non-negative pressure. Right, so if I use that in the first of Friedmann's equation, so using that in this equation here, we said the energy density is positive, the pressure is not negative, so that means that A dot dot, what can I say about that? What can I say about A dot dot?
Equals a negative constant multiplied by A.
It must be smaller than 0. Right?
Why can't A be not non-negative?
A is the scale factor. It cannot have coordinates which are negative, right?
Okay.
Right. This is what multiplies all the coordinates, right? dr times A, that's a negative, that doesn't make sense.
So A dot dot being negative would mean that the universe is expanding, but it's slowing down?
Yeah. Yeah. Now we know, so if I plot it, right, that means, this is the time, and this is A of t. Right? So if I plot, now it's t0, right? This is now. Right? So if I have to plot it, right, it means that it goes like that, right? Now we know from Hubble that the universe expands, right? So the universe expands, that means that A dot is greater than 0. Right? Scale factor that multiplies the coordinate, they inflate. So A dot is greater than 0. Right? So A dot dot's more than 0, that means that indeed the universe is decelerating in some sense, so that the rate of expansion goes down. Right?
Asaf,
Yeah?
can you explain again why A dot dot is smaller than 0?
Yeah, of course. Just look at the Friedmann equation, right?
From
Just
the
plug in the
algebra?
Friedmann equation. I said rho is non-negative. P can be 0, but not smaller than 0.
Oh,
So everything here must be a minus sign. A is a positive because it multiplies all the coordinates.
But we must assume that rho is non-negative.
Yeah, we have there is some energy in the universe, right?
Okay, but is there a physical meaning to a negative rho?
Well, that's what we say. You can think of it in terms of the vacuum. Vacuum will be that P is equal to minus rho. It's something which I don't know if there is a simple way of thinking of that. So I'm talking now about regular, I assume lambda equal to 0, so no vacuum energy, just matter and radiation, the things which we think we understand, right? So we know that A dot is positive. We know that A dot dot is negative, which is pretty much what we'd expect to be, right? Because the universe started from some expansion, right? But there is gravity, and gravity attracts things back. Right? Remember, we're really looking at the solution to Einstein's equation. Right? Friedmann equations are a solution to Einstein's equation. Einstein's equations represents gravity, and gravity attracts things back. So the universe expands, but gravity pulls it backward. Right? So if it's accelerating now, that means that in the past it was expanding at even faster rate, right? So it must have been going to something like that. right? When we evolve backward in time, that means that sometimes in the past, the universe, the scale factor must have been smaller and smaller, right? And of course, when a is equal to 0, that's called a singularity. Now, had we have a dot dot exactly equal to 0, right? If we had a dot dot equal to 0, what will we get? So if a dot dot was exactly 0, what will happen to the universe in the past? Simply proceed as a straight line. It's actually a bad drawing because I didn't mean it to be drawn such that it will end exactly at that. That's a dot dot is equal to 0. What is the time? Had a dot dot exactly been equal to 0, what is the time from the time that a was equal to 0 until today?
The time of the entire universe.
Yeah, and what would that be equal to?
Not 13 billion years?
No. In the equations which we wrote already, which we derived. I actually wrote it right here, if you can see. If a dot dot is equal to 0, right, and I proceed with this slope here, how far in the past would I get? Right? Think of it for a second. With just 1 over the Hubble's constant. Yeah? Right? So 1 over the Hubble constant give us an upper limit in this expanding universe, an accelerating universe, decelerating universe, sorry, on the lifetime of the universe. Now, since a dot dot is negative, that means that the actual age of the universe is slightly less than 1 over Hubble's constant. Right, you all with me? Not so? What's the definition of the Hubble's constant?
The rate of the expansion of the universe.
It's just a dot over a, right?
Yes.
This is just the slope of this line here, right?
Asaf, can I ask a question?
Yeah.
But if we wanted the fact that the expansion parameter that a goes to 0 in a non-linear way, I would assume that the reason for that is because if we go too far into the past, then the Friedmann-Robertson metric would not be valid anymore, right?
You're confusing a few things, right? The reason why we have this sort of parabola shape is because we have a dot dot here, right? Because the Friedmann equation basically is a second order differential equation, right? Not the first order, right? If we put a dot dot to be equal to 0, we're left with the first order differential equation. And then you have a linear solution, essentially. Now, you're saying something different. You're saying, okay, when a gets closer to 0, right, we get some sort of a singularity, then at a certain point, the laws of physics, I mean, this is what we do here is called classical general relativity, right? Then you'd say at a certain point, using Einstein's equation may not be valid anymore. And you would be right. I mean, this would occur once the density will get so high that the energy density will exceed what's called the Planck limit. Essentially, at that point, quantum mechanical effects will have to take into consideration, and that's when you have to switch to a theory of quantum gravity, right? But that will happen, very close by here, right? We're talking about a tiny amount of time after this Big Bang. Now, again, I want to say something about this. Obviously, this point here when a is equal to 0, well, that's obviously what's referred to as the Big Bang.
But the thing that what bothers me is that it's not being drawn at t equals to 0. So basically, we assume that the Big Bang could have happened at any time, and it's just arbitrary what we call it t equals to 0.
How do you measure time, right?
Yes, okay, I understand now.
Now, I do want to say something, because this is something which many students get confused about, right? I mean, okay, the Big Bang essentially refers to a moment in the history of the universe where the scale factor was equal to 0. And what is the scale factor? This is the factor that multiplies all the spatial coordinates, right? So, you think of it like we have a grid of coordinates. Now, in the past, right, all this was getting smaller, right? So in the past, we had the same grid, which was smaller, right, and even smaller, right? So the grids got smaller and smaller and smaller. So, we're saying that the universe expands, right, as time goes by, right? So as time goes by, the coordinates expand, right? Now, that does not mean that the universe had to expand into anything. It could still be infinite at the time of the Big Bang, right? Because the analogy that you can think of is a photocopying machine, right? If you take a photocopying machine, right? We use that a lot when I was a student to take material from each other, right? Then you can shrink, right? You can use the shrinking option. So you take a page and you shrink it. And now everything is being squeezed and you have like a smaller fonts, right? I don't know, 50% of the original size, but you did not lose any information, right? Everything just became denser, all the information. Now you can do it again. So everything will be smaller and smaller. Eventually, when you take a copy machine, eventually you will get to the resolution of the printing, so you cannot go below that, but here there is no restriction, right? Also in a copying machine, there is always a restriction on how big the page that you put in can be. But here you don't have any resolution, right? If you take an spatially infinitely big universe, you squeeze it into 2, right? Infinity divided by 2 is still infinity. It's just more dense. So that's the situation that we have here. We didn't say, while the universe expands, it does not mean that it expands into anything that was there before. Right? There is nothing in there before.
So how could, okay, last question, I'm sorry. But if we assume that the Big Bang was, all the matter of the universe was condensed into a singularity, how did it not just collapse into a black hole? Why did it expand?
Well, that's a very good question, right? That's a very good question. Maybe we are inside the black hole. Now you can let your imagination flow, right? Maybe we are. I don't know, right? We got a solution to Einstein's equation. What did we do, right? We derived Einstein's equation, then we solved it, right? We got a solution which represents a homogeneous and isotropic universe that solves Einstein's equation. And that's the result that we got. Now I tell you that obviously one thing which we know for certainty is, once things, we can trace back the evolution of the universe quite close to the Big Bang, but we cannot really trace it back all the way, because when the density becomes too large, then that's where quantum gravity effect becomes important. And that is not part of anything that we did. We did not do anything related to quantum mechanics in this course so far, right? So we know that there must be some effects which we're not, there are some other effects in black holes which I did not discuss, but okay. There are some things waiting for advanced general relativity course, which we can have if you really insist, and ask Yossi about. But you see the point, right? That's where the limit of current knowledge in physics exists. Right? We simply don't know. And what causes that, whatever happened there before, what causes that to expand? We don't know. We just know it's there. And, you know, when we go, you know, the experiments that are being done in CERN, you know, going backward and backward, increasing the energies essentially mean going backward and backward in time to the times where the energies were higher and higher. That's where it's connected to particle physics. And possibly there were new particles here that don't exist today. Actually, we know that there were new particles. I'll talk about that maybe in the last lecture. We know that there were other particles there. Right? Cool, isn't it? Okay. Now that was the past. But what about the future? So let's look back at the future evolution. So as it turns out, the future evolution also depends on this parameter K, and is different for open and flat universes than for closed universe. So we first have an open and flat universes. So for open and flat, we know that K is negative or 0. So we go back to the second of Friedmann's equations, which is written here. And so from the second of Friedmann's equation, we can write it down as A dot squared. Just going to multiply it by A squared, right? So we have an A dot squared is equal to 8 pi G over 3 rho A squared. And there was a, remind you, there was a minus K, but we said that K is negative or 0. So I can write it down as plus absolute value of K. Now again, since we're assuming that the energy density is non-negative, so for rho which is greater than 0, that means that the right-hand side is always strictly positive, right? So this must be always greater than 0 as well, which means that A dot in the future is never 0. It's always greater than 0, always, in the future. Now we know today that A dot is greater than 0 because we know that the universe expands, right? A dot greater than 0 today. So it's an expansion of the universe. Which means that A dot is always positive. It will stay positive at all times. A dot will always be positive.
Saf,
Yeah.
you say in the future A dot is always positive, but you said also the universe is decelerating.
Yeah, but okay, we'll get to that. It is decelerating parameter. A dot can change its value with time, but it cannot go below 0 in that case, in that specific case where K is open flat universes. And that follows directly from Friedman equation, from the second Friedman equation. So for this specific case, under the assumption that rho is always positive, A dot is always going to be positive. It can change its value. A can change its value, but A dot is never going to be 0. And what does it mean that A dot is always going to be positive?
That the universe is accelerating?
The universe will continue to expand, right? A dot can go to nearly 0, right? Doesn't have to accelerate and decelerate, right? It's the rate of change of the expansion itself, right?
But observations say that the universe is accelerating, right?
Yeah, we'll get to that in a second. This is kind of a fake because I assume that lambda is equal to 0 here. Right? So that means that the universe will continue to accelerate forever, to expand forever. The universe will continue to expand forever. That means, that it's not only going to be spatially open, but also temporally open. There will be no end to the universe, as we know. Unless, of course, sometimes in the future, something will happen which will cause the energy density to become negative. But this is not something which we understand or predict in any way. Okay. If something will happen that cause the energy density to become negative, and there are theories which predict that because this again relates to this vacuum energy. But as long as it's not there, then the universe will simply continue to expand forever. That's actually quite interesting meaning when you think of it. I'll discuss that later. Now we can actually calculate how fast is it going to expand. So how fast will it expand? So again, we wrote down the energy conservation equation. We did it last time. Zero is just blah blah mu t mu 0 is just minus d0 rho plus, minus 3a dot over a rho plus b. Right? We wrote this last time, but it's really just a conservation of energy. T mu 0. Now this, in fact, is equal to d over dt of rho a cubed is equal to minus 3a dot a squared p, which you can get right away by simply expanding that left-hand side, right? Just give us d0 rho a cubed plus 3a squared a dot rho. Just move to the other side, and that's it. Right. Now again, the right-hand side can be either 0 or negative. Right? So these are smaller than or equal to 0. So we can write down d over dt of rho A cube smaller than or equal to 0. So if we say that the universe expands forever, so if A goes to infinity, right, this equation tells us the only way to compensate for that would be if rho A squared goes to 0 faster.
Wait, did you just multiply both sides with A cubed?
Yeah.
Then how did you bring the A cubed into the derivative if it's not constant?
Because it's not constant, I can put it in derivative, right? I have here A dot. I'm not sure that I'm with you. Ever d0t, d0 rho, right? So d rho over dt minus 3 A dot, it's the A dt, or A rho plus P, right?
Yes.
What's written here, right? D rho over dt, right? This is equal to d0 rho times A cubed plus rho A squared times 3A dot.
Okay. Yeah. Okay. And
So this equation here and this is the same equation, just written in a different way. Come on, guys. This you can do. Yeah? Okay?
yes, thank you.
Okay. So we ended up with the equation that d over dt of rho A cubed needs to be smaller or equal to 0, but we say that A goes to infinity. So the only way this can be is that if rho A squared goes to 0 in this limit where A goes to infinity. It needs to go to 0 faster. Right? So looking back at the Friedman equation, right, we find out that we take this equation. If I take this equation, if I take this equation, right, that means that when A goes to infinity, we must have that A dot squared goes to K. So when A goes to infinity, right? So for K, which is equal to -1, right, then we have the limiting value that A dot goes to 1. Right? So for an open universe, right? And when K is equal to 0, then we end up that the A dot goes to 0. So the universe will keep expanding, but slower and slower. Right? So this can be any solution at A of t, right? Could go to t to the power alpha with alpha which is smaller than 1. Can be greater than 0. So we end up, if we look back at this plot, right? Time and A of t, this is today. And then in the future, we'll have, in that case of an open universe, A dot goes to 1. Right? So it will go something like that. Right? If it's flat, can be anything. But any power law is less than 1, so it could also go lower. Flat. Any power law which is smaller than 1 will work out. What about closed universe? Okay, it's essentially the same thing, right? So for closed universe, we have that k is equal to +1. So again, I'm going back to Friedman equation, so I'm going to use the second equation. So now actually I'm going to use the same equation. So a dot squared is 8 pi g over 3 rho a squared, and then the -1 will be here. A dot squared is equal to 8 pi g over 3 rho a squared -1. Now, the argument that rho a squared goes to 0 when a goes to infinity that we derived here is the same argument because it's based on conservation of energy. Right, so rho a squared goes to 0 when a goes to infinity. That is still valid due to energy conservation. But that, of course, means that we have a dot square goes to -1, which cannot be. Right? But then a dot square goes to -1. So how can it be? So what's the solution?
It must be shrinking back.
Exactly. A never gets to infinity. There must be some maximum, right? Some upper bound. And then, so there must be some 8 max, right? So when A approaches A max, then we get again the second Friedman equation, so the first of Friedman equations. Right? States that A dot dot is -4 pi g over 3 rho plus 3p A max. Right? But this is always smaller than 0, which means that A dot dot is finite and negative. Okay. And so once you reach A max, then the universe starts to max. Once you reach A max, the universe starts going back. And so essentially, we'll have to end up in this thing which is called the Big Crunch. Which is closed. So again, a closed universe, under the assumption that it has a positive energy density and non-negative pressure, is also closed in time, not only in space.
So there is no real meaning for a direction of time, no? Because we could just say that the Big Crunch is the Big Bang from the other point of view.
There is a meaning. Time progresses in one direction.
But how can you tell if
I can just tell the future.
How? I mean, wouldn't it be symmetrical in the direction of time? If I would have shown the Big Crunch and I would have played it back in reverse, it would have seemed like the Big Bang, no?
No, not necessarily. I didn't say it's a symmetric. Right? I didn't say that they evolve in a symmetric way. I just say how they will evolve at the end.
Oh, as in that the curve of A would be a proper parabola. It would
No,
just be a hump.
I didn't say it's a parabola. Yeah,
Okay. Yeah. Okay. I see.
check actually. I didn't really do the calculation. I didn't say anything about what happened. I didn't say anything about it being a parabola. I just say that, on the contrary, right? I just say you try to plot it such that it's not exactly symmetric. Right? The one thing which is for sure is that such a universe would end up in a very different way than the universe, the flat or the open universe. It will have an end. So that's another reason why we're interested in knowing whether a universe is flat, open, or closed. To be able to predict our fate, whether we will dissolve into nothing or we will just squeeze back into nothing. Okay. Okay, the situation in fact is more complicated than that, because this we assume the universe that has no cosmological constant. Right? Now the measurements that we have today actually show that there is a cosmological constant. And because there is a cosmological constant, the universe currently is accelerating, not only expanding, but accelerating. So not only that A dot is greater than 0, also A dot dot is greater than 0. And although we know nothing about the nature of this dark matter, there are many theories, but nobody really knows. There's no any consensus or anything. And so unless the energy density will somehow reverse its sign at a certain point, namely the universe will start shrinking, to the best of our knowledge, the universe will continue to expand forever and accelerate forever. It's quite interesting because when you think of it as the universe accelerates, right, the observable part of the universe, right, we can only see galaxies that emitted light. I mean, it has very interesting consequences, which I'm not sure that everybody is realizing. It's definitely not for the first time to see, right? If we say that the universe, has a finite time, finite age, I said the universe may be infinitely big, but there is the observable universe, right? Since the speed of light is constant, it's just c, right? Then there is a maximum distance to which we can see from the beginning of the universe, which was this c times the age of the universe, right? There may be something out there, but we cannot see it because light from there never reached us. Now, if the universe is accelerating, that means that this horizon, the observable universe that we can see, actually is getting smaller and smaller as things are accelerating away from us, which means that in the future there will be less and less galaxies observed. If somebody, astronomers, would read astronomy textbooks, millions of years from now, if for any reason they will open up, archaeological textbooks from those days, and we look at they'll see many galaxies, and they will not know what we're talking about because they couldn't see any of them. Right? Think of it. It's quite cool to think of. All right. I should just say that just for completeness, that, okay, so we spoke about 3 types of energies in the universe: matter, radiation, and vacuum. There is this curvature, which appears as a term in Friedmann's equation. So it's often, one can write down a fictitious energy associated with the curvature. So we can think of a curvature energy. Essentially, you can define rho curvature to be defined as minus 3k over 8 pi g a squared. And that means that, of course, the corresponding density parameter would be omega curvature would be minus k over h squared a squared. This is a curvature density parameter. Then using this new definition, we can write down the second of Friedman's equations. So Friedman equation and the same equation that we're using, right? This one, no, the same as this one is the K. We simply write it as h squared is equal 8 pi g over 3, and then sum over I of rho I, where rho I referring to rho matter, rho radiation, rho vacuum, and rho curvature. There's also rho lambda. And the same equation we can simply divide by 8 squared and simply write it as 1 is equal to sum over I of omega I. One thing is that, you know, the energy density is here. When I write it like that, it's kind of giving them all interpretation of energy density, all the components that we can have in the universe, but it's not the regular energy density that you're used to, right? Only the matter and radiation energy density are ones that we can, for certainty, assume that they are positive. The rho vacuum and the rho C, they don't have to be positive. Just a simple way of writing it. It's really Friedman equation. Right. Rho M and rho R are positive, but rho lambda and rho C can take any value. That's quite confusing because there is no real intuition, I think, on what it really is. All right, questions? Okay, then I think that it's about time to talk about this thing which is called the cosmological redshift. We already introduced this gravitational redshift, right? We said that when photons get out of gravitational potential, they essentially lose energy, so they're being redshifted. Now here, this is something which is completely different, right? Now we have something which, well, what we really have here is that the coordinates are changing with time, right? We have this time dependent of the scale factor, A of t, right? The scale factor, A is time dependent. Right? Which means that the FRW metric is not a static metric. Now, the A of t multiplies all of the spatial coordinates. So if we speak about any proper distance, it has to change with time. So any proper distance, right, L of t, changes with time. Right? Proportional to A of t. So L of t is just L0 times A of t. It's linearly proportional to A of t. So L0, right, is the co-moving distance between any two static observers. Right, so if I go back to this picture that I drawn here, right, So I have two guys, right? Each one is standing, let's say, at the edge of its point. As time goes by, right? They're static. They're co-moving, right? But the distance between them increases linearly proportional to A. Right? So what I'm showing here is that the proper separation between two observers which are located at constant co-moving coordinates changes with time. So if I draw the coordinate separation between these two observers as delta r, well, let's copy that. So the proper separation. So if the coordinate separation the delta r, right? Then the proper separation is delta L, just A of t times delta r. That's exactly what's shown here, right? This is r I, this is r I plus 1, right? So we have a delta r here. This hasn't changed, the coordinate hasn't changed. But the grid is being stretched. Because A of t is the scale factor that multiplies everything. Right? So each of the two observers will attribute this change to a velocity of the other one. Right? So each observer will attribute to the other the velocity. Right? Delta V is just d over dt of delta L, which is just A dot delta R, which is just A dot over A delta L. Now, the analogy that is often given is that of a balloon. Think of a balloon, then you draw some dots, and each dot represents a galaxy, and then you inflate air into the balloon. Right? And then these dots, they recede away from each other simply because the balloon is being inflated. On the one hand, there is some good analogy because it's easy to visualize what happens, the expansion of the universe as due to, universe being stretched. The reason why I do not like this analogy, and I often don't use it, is because the balloon is expanding into an already pre-existing space. And the universe does not expand into anything. It just expands, point. But the outcome is indeed that when you're looking in each direction, right, you're seeing that each galaxy is moving away from us, receding away from us at some velocity, delta V, which is A dot over A times delta L. So if you're not thinking, let's say, of some electromagnetic signal that is crossing us. So this guy wants to send this guy. Actually, I should have brought this. So this is an alien. Right? So it has an alien. So he wants to signal us. This is me here, right? So he wants to signal something, so he sends photons, right? Actually, maybe I should do it in a different color. Sends a green photon here. Want to tell me something. Right? This alien that lives in a different galaxy. Hey, what's your name? Right? So the transient time, delta t, right, is just delta L over C. The transit time of the electromagnetic signal. Right? And let's assume that the frequency here is omega. So the frequency as measured by the first observer is omega. Now it's actually quite lined here, but I should have brought it here. Right? He signals to me here. The thing is that by the time I receive the signal, right, the signal travels to me, right? But time also progresses, so actually the signal travels in this direction, right? This is space, and time goes up, right? This is time. Now, since from point of view of the alien, right, I am receding away with some velocity delta v, the emitted frequency. Since I'm receding away with some velocity delta v, then the measured frequency, right, will be Doppler shifted, right? So measured frequency, omega plus delta omega, where we have that delta omega, right, over omega is just minus delta v over c. This is just minus a dot over a delta L over c. So this is just a minus a dot over a delta t. This is simply a minus delta a over a. Right? I just assume infinitesimal changes, so I neglected the high order effect. So integrating that is immediate, and that just means that omega t times a of t is constant. Do you follow what I'm doing? Right. In other words, it means that omega t goes as a of t to the minus 1. Now I've made a mathematical step here by assuming what I did here. This is locally true, but then I assume it's globally true, and that is true provided the universe is indeed homogeneous and isotropic. I actually made use of the homogeneity of the universe in transferring from the local frame to global result. So if a photon was emitted with the frequency omega 1, photon emitted with frequency omega 1 is observed, of course, sometimes later at a lower frequency, a omega 0, So just omega 0 of omega 1 is just A1 or A0. And the reason now, the calculation is very similar to the calculation of a Doppler shift, but it's not really, because the Doppler shift is based on it occurs when the two observers are moving with respect to each other, right? Here it is based on the fact that the scale factor is changed between the time of emission and the time of observing. So even if, even if the scale factor, if A of t, let's change color, right? Even if A of t looks like that, and this is the emission time, this is the observing time, T0, there would still be a redshift, although at the time of emission and the time of observant, there is no motion. Well, there will not be any Doppler shift. Okay? Because it's entirely based on the fact that the universe, that the scale factor has changed between the time of emission and the time of observation. Yeah.
Can't you say that the observers are moving with respect to the photon, and it's again Doppler?
Well, that's exactly what I said. When I derived this this equation here, I actually used the same formula that to be used that is being used when you do a Doppler shift. The observers are not moving, right? They are, they're steady in their coordinates. I'm not moving. Our galaxy is not moving. It's the universe that expands, right? We're not moving. We're at the same point in space all the time. We're not moving anywhere. It's just that the space itself is expanding. And so the distance between us and the alien, which was small distance in the past, is now getting larger and larger as time goes by. But that is because the scale factor A of t that multiplies all the coordinates. Because it had some value in the past and now it has a bigger value.
Yes.
Okay. Now, in cosmology, right, we don't look at the, we don't know what is the value of the scale factor, and we don't look at the frequency. Rather, we talk about the redshift. So the redshift, is denoted by Z. It's called the cosmological redshift. And again, it's between two events, emission and absorption, and is defined by the fractional change of the wavelength, right? So Z is defined, it should be cosmological here, as lambda 0 minus lambda 1 divided by lambda 1. Remember, 0 is today, and 1 is at the time of emission. This is just A0 over A1 minus 1. Lambda is the wavelength, the photon. Okay, and it really tells us how much the universe has expanded since the time of emission until of the photon that we're observing until today, which is when we're seeing this photon. Now, what is the advantage of using redshift?
We can use it to calculate the age of the universe.
That as well, but no, the first advantage is that this is something which we actually measure. How do we measure redshift?
Spectrography?
Right? What did you say?
Spectrography?
Spectrometry. Yes.
Spectrometry.
we are assuming, that we don't assume, right? The matter in the universe, that there are specific emission and absorption lines, and we know they're exactly the wavelengths of these absorption lines. And and we know for the different elements they have these specific emission and absorption lines at very given wavelengths. Now, when we're looking at other galaxies, we are seeing these emission and absorption lines in the spectrum of the light that we see from other galaxies. That's how we know that all the stars have the same hydrogen and the same processes, or they're everywhere. Only we're seeing these emission lines being shifted, constantly shifted towards the red of the spectrum. Okay? So the difference in the measured wavelengths minus the one that we expect, this is exactly the redshift.
But how would we be able to differentiate between the cosmological redshift and a gravitational redshift? Because the gravity well of a galaxy would be quite big. So there would be some contribution, no?
There will be a contribution, you're right. But it won't be as big as you think, right? We calculated the gravitational redshift from the sun, for example. Right? If you're talking about, and this is one of the things you did in your homework, I think, in one of the problem sets. It's not that big. But yes, you're right. In reality, we have both. Right? Remember that when we speak of distant galaxies, right, we don't see individual stars. We're mainly seeing light from the halo of the galaxy. Right? So we're really averaging. And yes, at the end of the day, we do need to consider both effects. Although this effect, when we speak of galaxies, distant galaxies, this effect is much, much stronger. Essentially, by the way, this is, that the Hubble Space Telescope, right, which we already spoke about, is now being replaced. The next generation would call the James Webb Space Telescope, JWST, and is sensitive to the infrared. Why is that?
Because of the redshift?
Because of the redshift. The main reason is that in order to be able to see galaxies very, very far away, right, we can no longer see the optical light from the galaxies because it's all being redshifted towards the red. So we put a detector in the infrared to be able to see them. So the ability of the new generation space telescope to detect further galaxies is much better than the one of the Hubble Space Telescope.
But if we would see those galaxies from very, very far away, we would also see them from very, very back in time, right?
Exactly. So there is a period in time, we'll discuss that, but it will be next week. There was a period in time when there were no galaxies. They had to have time to form. So one of the scientific goals, for example, of the next generation space telescope is to study the formation of the first galaxies. Now you're right. The definition of the redshift really helps us replace the coordinate time. Rather than time, we're looking at the redshift. So basically today we're using redshift to replace the time coordinate. Redshift Z replaces the time coordinate. So yeah, the higher the redshift means further back in time, which really means that when the scale factor was much smaller. Now there is one more thing which I have to cover before we go. Okay, so we had this derivation for photons. Now we can do the same for massive particles. So the same derivation, or similar derivation, applies to massive particles. So again, think of two observers, right? One would be me, and what will be the ln, right? And which are separated by some proper distance, right? Delta L is the proper distance between us. And let's say that there is a particle that passes, so there is some spaceship that passes through the first one at some velocity v. Right now, when it comes to me, right, time has passed, right? So time is going up. So by that time, I'm a little bit further away, right? So the velocity, right, delta u, I'm not confused here. So my velocity, delta u is just a dot over a delta L. So just a dot over a delta and t v delta t. So again, just v times delta a over a. Now, from my perspective, from the second observer perspective, let's say it's me, from my perspective, the velocity of the particle in the spaceship, the way I plotted it, right? I have to use the addition of velocities. So v prime is just v minus delta u divided by 1 minus v delta u. That's the relativistic version, right? So for small delta u, this would be a v minus 1 minus v squared delta u plus O of delta u squared. So this is just v minus 1 minus v squared. And delta u is just v times delta a over a from here. Let's see. All right. And so we can simply write this as a delta v, right? V prime minus v is just a minus v divided by 1 minus v squared delta a over a. And this we can integrate. Which will get us that the momentum is just v divided by square root 1 minus v squared. It's just some constant divided by a. Which means that the magnitude of the momentum goes as 1 over a. Which again makes sense due to the expansion. So due to the expansion, P 1 over a. So if it's a non-relativistic, then V is proportional to P, right? We'll also go as 1 over a. So we're actually saying that the particle slows down. Which again, so it makes sense. Now I'm throwing a ball at you, but we are, kind of receding away from each other. So the ball slows and slows and slows and slows as it progresses. Right? And that's a real slowing down, right? Because the universe expands. So, if you have a gas there, the gas expands and it kind of slows down. It's a real expansion. It's a real slowing down. All right? Okay. I think I ran out of time. Any questions? Any questions?
I have one, but I'll wait until if anyone has another one, because I want to ask something of the record.
I also have a few, but they're on homework, so.
I will give you another set of homework. I checked out the calendar. We have 2 more lectures next week, and then there is no lecture because of something. I don't know what it is. Shivasa Betamuz. Whatever. So we have 2 more lectures next week. We will complete the discussion about cosmology. I'll see if I have some time. I may say a few words about gravitational wave, but I may just skip it. But we will continue the discussion about cosmology because there are very many fascinating things around here. So at least we'll cover some basics by next week. Bottom line is today I'm going to hand you the last problem set of the semester. I'm not planning on giving you another problem set. Please hurry up if you have any leftovers. I will get less and less flexible as the semester approaches an end. Okay? I won't let you, and I told you that, and I'm repeating that, I won't let you submit all the problem sets 1 week before the exam. I will not accept it. I can give you some extension now, but if you come to me with 3 problem sets, 4 problem sets you haven't submitted, and give it to me a few days before the exam, I'll tell you I'm sorry, time is over. So don't push it. If you do need a real extension because you have some local problem, that's fine, there's no problem. Okay, but now the semester is getting to an end, and I'm sure that you're busy and you're worried about exams and all that, so don't push it. Just do what you need to be successful. All right, so I think I can do a stop sharing. I can do a stop recording.